Hello, I'm Mike McCulloch. Today I'm going to try and explain to you why I have a different view of Redshift from the mainstream. So as you may know, the usual idea is that as astronomers look further and further out into space, because the universe has been expanding and is expanding, the further we look, the faster stars and galaxies and supernovae are moving away from us. And so rather like the Doppler shift, the waves, the electromagnetic waves emitted by their atoms are getting to us with a longer wavelength and are therefore redshifted. And this is why the further we look away, this is supposed to be why the further we look away, the more redshifted the light from atoms is getting to us. So just a reminder of a bit of atomic physics. So this diagram shows an atom. So the nucleus is in the center, the black dot there. And in the Bohr model of the atom anyway, which is the simplest kind, the simplest model, the electrons orbiting around the nucleus, and because their quantum waves have to fit within their orbits, they can only orbit on certain allowed orbitals, which are shown here by the orange circles. Now, if it so happens that a photon comes along, hits an electron in this atom, it can get enough energy to move from a lower orbital to a higher one. And then what happens is that it tends to fall back down from that orbital to the bottom or a lower orbital. And in doing that, it has to emit a photon of light. And the photon of light has an energy which is given by h, Planck's constant, times its the frequency, or hc over lambda, which is, or L here, which is a wavelength of it. And now if the electron falls from the second orbital to the first, you get a bit of energy released. If it moves from the third orbital to the first, you get more. So I've tried to show this in this diagram. So the electron that's just moved from orbital 2 to 1 releases longer wavelength, lower energy light, blue light, shown by the blue curve. And an electron moving from a much higher orbital to that lower one releases a lot more energy, because a lot more energy is being lost from dropping from very high up to very low down, a lower orbital. So you get red light coming off. And each atom has a characteristic spectrum of light that they emit like this. So the light emission is kind of quantized into different energy levels, and they can measure this. And this is why when they look at distant stars, they see them emitting less energy as the electrons transition between these levels. And so what they imagine is that the atoms are the same in the galaxy. The physics hasn't changed, but the light is instead being redshifted by the motion of the atom away from us. But I have a different view, and this was speculated about by Halton Arp back in the 90s, I guess, with his book Seeing Red. Although he didn't have a mechanism for it, he suggested, well, he thought the observations, and he was very good at spotting these observations, he was a very good astronomer, the observations seemed to show that this redshift may not be due to the Doppler shift, at least in all cases, because he saw some apparently very high redshift galaxies attached to very low redshift ones. So he was saying that the data seems to show that redshift is intrinsic, but he didn't know how it could be. Well, I think quantized inertia can give a reason for this, and I've tried to show this here. So look at the bottom circle for a minute. This is us in our universe here. So the sun is in the center, and we may see an atom fairly close to us, which is emitting normal radiation as its electrons transition between the different levels. We see this, it could be a helium atom or something higher up. it's emitting a particular spectrum, and it's pretty much what we'd expect. But then we look at atoms which are far off, and I've shown that with the circle above. This, we're looking at an atom which is much further away. Now, for this atom, we're seeing the light from it when it was, well, when it existed millions of years ago, and, well, billions of years ago perhaps even. And back then the universe was much smaller, and I've tried to show this with a smaller circle. This particular atom that's far off has a smaller universe surrounding it, and quantized inertia predicts then that the physics will be slightly different, because the inertial mass, one way to think of it is that the inertial mass of the electrons orbiting the nucleus will be lower, because in this smaller universal cavity more Unruh waves will be disallowed, and in quantized inertia Unruh waves form inertial mass, produce inertial mass. So the centrifugal force, the inertial mass of the electrons orbiting the atom will be lower, the centrifugal force will be lower, so the atom will be smaller, the electron orbitals will be smaller, so the transitions will release less energy. And instead of the Doppler shift, this could explain why these atoms are emitting redshifted light, because they're in a smaller universe, the atoms themselves are smaller, the electron distances between the electron orbitals are smaller, and yeah, so that is an alternative to for explaining redshift. And I think it makes sense, because it also agrees to with Halton Arp's observations that some galaxies have a high redshift when they're attached to lower ones. It could be that this is new matter which is in a smaller informational universe, and the atoms are different. Okay, so this needs far more rigorous calculations, of course. I started some, and you can see those in my book, Quantized Accelerations, some initial calculations which seem to agree with some of Halton Arp's quantized values for redshift. So you could have a look at that. But anyway, I hope you've enjoyed this short, and I look forward to making another one for you tomorrow. Goodbye.